The following presentation is a tutorial into how to use Nmap or Network Mapper. For this tutorial, I'll be using a PowerPoint to guide us through the objectives that we have planned for this lab. For the lab itself, I'll be using Kali as our offensive distribution and firing up Nmap from within this system. And in addition to this, I'll be utilizing the Linux target that should be configured within your environment. Of course, if you don't have this particular setup, you can use Kali along with any other type of system. In my particular example, I'm using a VMware workstation, but the same environment can be easily replicated using VirtualBox. This is just a proof of concept, and again, it can be replicated pretty much by anyone with Kali and another virtual machine as the target. To get things started, I'm going to fire up the PowerPoint. So a brief overview, so we will go through definitions, what is the goal of using Nmap, a little bit introduction about Nmap itself, the open system interconnect model, the TCP/IP protocol, three-way handshake, then we're going to go into Nmap usage, different types of scanning, examples, some useful tips and lessons learned from previous experiences, and then we're going to delve into using the Nmap script engine to provide some more advanced scanning features and enhance, to show the enhanced capability of Nmap, not just as a port scanner, but perhaps as a utility that we can use for brute forcing different credentials, vulnerability scanning, exploitation, and so on. To get things started, definitions. The process of identifying open ports, running services, versions of applications, operating system, MAC address, and potential host discovery can be referred as intelligence gathering, scanning, enumeration, and reconnaissance. So all of these different terms basically lead to the same objective, is discovering information about your target of evaluation. So the purpose is, again, we're discovering the live host and getting information that can help us during the vulnerability scanning process. Essentially, we're identifying different attack vectors as well as different communication channels that we can remotely examine the system using those channels. Okay. There is actually an interesting video that simulates that a discovery scan, so a simple port scan, could be actually a precursor to an actual exploitation attack. And if you'd like to review an example of that, simply go to the video provided in this presentation to Adrian's Iron Geek website. So we talked about the goal of the discovery, that intelligence gathering is open ports, running services, operating system, whether or not the target is live, potentially user accounts, misconfiguration. So for example, you have a weak OpenSSL implementation, older versions of software, including network topology. So what is the layout of the different systems that you actually are planning to evaluate? Nmap. So Nmap is actually the most popular network scanning utility that is known to date, at least in my opinion. It's a useful utility that pretty much any security professional, as I'm coming to find out, a lot of system administrators are very familiar with, or at least should be. So The utility itself is open source, which makes it attractive, especially for security programs on a shoestring budget or no budget at all. And the capability of Nmap actually has grown over the years. There's a lot of very information available, video tutorials, and the scalability and capability of Nmap is really limited by the number of people actually that support it. Being that the support is usually community-based, the possibilities are endless. So the ability of Nmap to find out information about a particular host is based on the premise that you can actually create IP packets from scratch and send them out using network communication methodologies and essentially interact with the target of evaluation. So there's most of the textbooks and reference material in different modules provide some guidelines onto using Nmap, but in my opinion, the most comprehensive and thorough manual for Nmap is actually on its creator's website, Fyodor. If you go to nmap.org/book, it will guide you to that reference manual. Nmap can be used for asset discovery, inventory, system administration tasks like verifying a particular port is visible or not visible, examining firewall configuration, potentially evaluating different products, and all sorts of creative purposes. There's something important to note that the Nmap project expands across different operating systems. So Nmap is available for Windows in the form of Nmap. So Nmap is the graphical user interface for Nmap. Also, Nmap is available on OS X and, of course, a variety of Linux distributions. It's important to note that the actual Nmap suite of utilities includes also NCAT, which is a valuable tool for data transfer, redirection, and can be used as a debugging utility. NDiff, which is can be used for comparative analysis of Nmap scans, as well as nping. So nping can be used for essentially packet generation and part of your response analysis tool set. Some fun facts regarding Nmap. When we are talking about movies and illustrating or simulating hacking, Nmap comes to be the most popular tool out there. And to prove this, it's kind of interesting. You know, Hollywood portrays this hacking as anytime there's a hacking scene, it seems like the most prevalent to show out there is Nmap, a basic pore scan. Some of these examples are listed in the presentation, which is perhaps a little bit of a fun trivia. So going into the user interface. The most popular user interface for Nmap is the command line. So very simple to use, comprehensive, flexible, and powerful. So the possibilities really with what Nmap can do are limited by our own imagination and experience and capability, of course. So the actual figure to the right presents what Nmap actually looks like. So in order to start Nmap, we can simply type in Nmap, provide a host. In this case, it's an IP address, and this is all it really takes to execute a very simple Nmap scan. The provided information, in this case, is a port number, the actual protocol used, if it's a TCP or UDP, the state of the port, if it's open, closed, filtered, and we'll actually talk a little bit more about the different port states, the service that it's running, the MAC address, and whether or not the host is up. And all this information is really obtained in about 56 seconds, excuse me. So going to the next slide. So the graphical user interface for Nmap is called Nmap. And Nmap essentially has the same functionality of Nmap, except it doesn't have the Nmap script engine capability, at least in this version that we have at the time in 2015. According to the author of Nmap, Fyodor, there are some plans for including the NSC script engine in some future versions. The other difference between Nmap and Nmap command line is the fact that there are some canned profiles. So with the command line, we'll have to know some of the usage, how to invoke some of the options. With the graphical user interface, you have some predefined scans that all we really need to do is use the drop down, specify a target, and click scan. Once we specify the profile, we can actually view the different options. It provides a graphical user interpretation of the hosts. Over here it looks like it's a little cut out, but it's a filter host, so we can filter a specific IP address. If you're scanning a whole range or subnet, we can go in and review the topology, which will tell us in reference to the host that we're examining what other systems are available. What is the topology for the network that we're examining? What is the connection between the systems that we are scanning if we're scanning a range? The host details, operating system, and so on. And then you have the capability to easily export and save scans. Okay, so really easy to use and navigate through. So how does actually Nmap does its magic? Well, it's leveraging some basic utilities like a DNS lookup, and what DNS lookup does is matches host name with an IP address. And Nmap actually pings the remote target with 0-byte packets to each port. What it does is, during this ping, it's trying to find out if there is a response. Most likely the port is open. If there isn't, then it's doing some other comprehensive calculations and determinations to determine if the port is filtered, closed, and so on. So the other thing that Nmap is capable of is it sends different packets with different timing to basically determine if the port is filtered, unfiltered, the version of the software that's running, and so on. And the biggest obstacle to Nmap is actually firewalls. There are some built-in firewall invasion techniques that we can leverage in order to bypass a firewall or perhaps examine the firewall configuration. And these may be reviewed at a later time. The importance of the open system interconnect model. And it looks like my image is a little bit skewed, but it should be okay for the sake of the presentation to just explain through it. So the open system interconnect model, it's essentially a theoretical universal model for interconnection and interaction between different hosts. There's 7 layers, and as some suggest, there's a layer 8, which is the user. So what's happening is we're essentially describing the data flow from one host to another, how the data actually travels between different communication channels, the physical, Cat6 cabling, the fiber optics, and reaching, moving from one system to another system. There is actually a very helpful YouTube video that walks through the OSI model that can be reviewed at your leisure by going to this URL. An easy way to remember the OSI model: please do not throw sausage pizza away. And what we're starting is with the physical layer. From the physical layer, it goes into the data, network transport, session, presentation, and application. And in the following slides, we're going to examine some particular examples of these layers. So the application layer, it's essentially the layer that the end user is interacting with. So we have layer labeled 7, so application layer is 7. The physical layer is 1. We're going to start examining each layer for 7 to 1. So the application layer, as I mentioned, is the one that the user closely interacts with. For example, a web browser. Okay, so we open up a program and we tell it, what is to be sent, create what needs to be sent, and we're capable of, leveraging functionality like resource sharing, remote file access, remote printer access, directory services, and network management. And one example of a user application, it's an email client. It's the SMTP protocol. It could be the ICMP, leveraging potentially ping. So we open up a command line, we send ping. These are anything that the user can use to interact with another system. So at the application layer, it's not that we are using the ICMP. ICMP is not at the application layer. ICMP is actually at the IP layer, the network layer. But we're using the window. We use the window interface, the application like a command line or a terminal to interact with another host. At the presentation layer, what we're doing is we're working with the format of the data. So at the application layer, the data is in a human readable format. It's in a format that a human can understand, read, and interact with. At the presentation layer, in order for the data to travel from one user and host to another, it needs to start to be translated into a machine readable format, plain ones and zeros. So at the presentation layer, if we're moving from application to presentation, the data is being dissected and stripped down into a format that really makes sense for the computer. If we're moving the data from presentation to application, we're really translating the data, making it in a format that a human can read. So some typical functions at the presentation layer are perhaps the data conversion, compression, some data encryption. Some typical protocols are actually the file extensions. So the JPEG, ASCII, PICTIF, GIF, and so on. So it's presentation of the data in a human readable format, or presentation of the data in preparation for traveling into the session down to the physical layer into a machine readable format. At the session layer, going from in a downward direction, we're establishing a connection between different processes on hosts. For example, that could be a client-server communication. So if we have a SQL client, we're connecting to a SQL database server. Well, we're establishing a session. So what's happening during this process is we have perhaps some login, we have some NetBIOS names, the remote procedure calls, the network file system tasks are initiated at this session layer. From the session, we're going to the transport layer. The basic objective of the transport layer is to assure that the data from the session layer is translated into essentially format that can be understood by network devices. In this case, what we are doing is assuring that the messages are delivered error-free in sequence with no losses or duplications. And the most typical representation of the transport layer is the TCP slash UDP port. So the destination, the source. So are we transferring, from an SMTP server to SMTP? How are we, establishing the communication between these hosts? What port are we using for that communication establishment? And then the network layer is essentially where the IP protocol resides. What host are we sending the information to? So we know in order to send the information from host A to host B, we have a particular port that we can set up the connection on. But who are we sending the information to? And this is where the IP address comes in. So once we identify, the sender, then we need to discuss, how are we sending this information? We're going to use what is the physical address. So not just the internet routable protocol for this system, but the physical address of the system. In this case, a typical example of the data link layer representative is the network interface card. Okay, so at this layer, we're identifying what is the physical location where the data needs to go to, instead of just the IP routable network or internet routable information. And then the physical layer is the actual transmission of the data into the very basic binary ones and zeros format. At this layer is essentially physical objects like cables, hubs, essentially fiber optics. It's the physical medium for transferring the information. There's a very useful, almost iconical video that shows the interaction between the OSI layer and different devices and how actually the internet works. And this video is available simply by going to YouTube and searching for the Warriors of the Net. Mousing over, you can see the URL if you're interested. Okay, moving over. So in the previous slide, we talked about the protocol data units. I mentioned data, segment, packet, frames, bits. So what's happening is we have an interesting process. So in the previous example, we started with layer 7, the application. And we're talking about the data traveling from host A to host B, starting from the application layer, from the web browser, type it in a URL. And then what is the interaction with the host B, perhaps the server, and what is the response from the server back to the host A or our client? So looking into the application, presentation, and session layer, the protocol data units in these layers are called data. So the data is essentially human readable format. Moving down to the transport layer, the data is converted actually into segments. This is where we have the TCP IP ports. Moving down into the network layer where we have the IP protocol, these PDUs are called packets. So when we refer to packet capture, that's referring essentially IP. We're at the network layer. Frames are at the data link layer, and switches operate with frames. The physical layer, the actual wiring, that could be the Cat6, the fiber optics, is the bits, is the raw, very, very raw data into binaries, ones and zeros. Important terminology to note, encapsulation. So it's basically flow of the data from the highest level human readable format to the lowest level machine readable format or bits. And then decapsulation, so moving into upward position from the very basic bits level up to the data level. If you'd like to find out more information about some basic concepts with respect to this OSI layer or OSI model communication, you can go to the INET Daemon website, which provides some good references and tutorials with respect to this subject matter. So an email example. So if we were to go in and using the OSI layer model or OSI model, we can examine how actually an email is being sent from host A to host B. So we can actually go into Firefox, and I have this loaded already. So the website is pucom.org, and what they provided is, I thought, was a very neat way to describe the actual communication. So in this animation, it's a representation of the OSI model. We're going to click continue, and it's basically telling us basic information about the OSI model and comparative to the TCP/IP model. Note, in this presentation we were talking about the TCP/IP protocol, which is different than the TCP/IP model. In the end of this flash tutorial, there's going to be a comparison between the OSI model and the TCP/IP model. These two models basically are the same thing. They do the same thing. It's describing how information flows from one host to another. The TCP/IP protocol is referring to essentially the transport control protocol and the internet protocol, not the model itself. So TCP associated with ports and IP with basically IP addresses, internet protocols, okay? It's important to differentiate between the two. So we hit continue, and we have application, presentation, the usual suspects. So what we're doing is they're going to explain each layer with an example. So the application layer is basically able to correlate. It's a parallel connection with the application layer between host A and host B. The same thing for the presentation. They have exactly the same function. Okay? So what's happening is there will be essentially an email sent from the red node here, from this host A into host B. And if you notice above host A, this red node, we have the OSI layer with the OSI model with the 7 layers. And then for host B, we have the same OSI model with the same 7 layers. So we're typing in and trying to send an email. So we're firing up, let's say, a browser, or perhaps email agent, Outlook, Thunderbird, whatever is being used. So at the application layer, we're typing in hello world. And what's happening is we're providing this email is being prepared, converts basically the information we typed in into a network format, and we can specify encryption, compression, and so on. So the actual human readable data is converted into ASCII format. Okay, from there what's happening is we're starting to figure out how we're going to establish a connection between this node and that node. So we're synchronizing data streams, video, audio streams, video session. In this case, for an email that's not relevant, but this, I guess, description is to give you an example of what other things can happen at the particular session layer. So adds a header to handle a session. So what's happening in this transport layer is providing reliability, flow control, fragmentation, port numbers between the different applications, running on the same node. So what we're doing is we're specifying, so email is running over TCP port 25, and it's important that this port will probably be used for the destination. So it will be received on the same port on destination. Okay. So down at the network layer, we're providing the addressing for the internet. So how is this email going to be routed, relayed over the internet from one host to another host? So it looks like in this particular example, we're using the IP address of 133.88.6.4 with a source port of 16.342. That could be for our client. And then we're telling the destination port is 25, so ports, transport layer, network layer, IP. IP is right here. So this is what's defined at this port, at this layer. At the data link, what's happening is, if you noticed, the MAC addresses, the physical addresses showed up. Okay, so now we know the physical destination and making sure that the data is related or relayed to the correct physical destination. Okay, so what's happening is the data is flowing from this data link to the physical medium. So this is the data is in its very, very basic format. So we went from frames at the switch level with MAC addresses down to bits at the physical layer. So the data is traveling up, and there is a router. So this is usually a typical symbol for a router that is relaying the information over a different network. And only the data link layer and physical layer require modification. So what's happening is the router removes the data link information and sends it up to the network layer. The router uses the destination IP address to determine where to send the packet next. So at the network layer we have an IP, so it gets this information, and then now it knows to move the data forward. So the data in this case was lost because the router was congested. So the sender transport layer timed out, waiting for acknowledgement, and the receiver transport layer. The sender's transport layer will retransmit the data, so it's basically a repeat. If the packet, for whatever reason, is not received, it's just a retransmission. So the same process all over again. So the router removes the data link information, sends the packet up to the network layer. It does its verification, IP address. It goes into the data link and physical, and what happens is that we're assuring that there's a reliable communication between the host A and host B. So in this case, when the sending layer does not receive an acknowledgement for the receiving layer, it resends the frame. So we're right here where we're working with a router, potentially router switch, and the frame needs to be resent from this device back to the destination host. So what's happening is we had encapsulation, so moving from data to bits. Now we're going to have decapsulation, bits converted back to data. So it reads the bits from the physical medium and sends the frames to the data link. We're moving now in upwards direction. Removes the data link headers, converts the frames back into IP packets, from the IP packets back into segments. From the transport layer, reassembles the segments back into data, and then from the session determines communication streams, prepares the data into a human readable format, and the user at the receiving end can now actually read the data using the particular SMTP client or perhaps a browser. So this was in a nutshell the communication that takes place or the intricate processes that take place behind the scenes when we send an email from one host to another. So I mentioned at the end of this flash tutorial that there will be a comparison between the OSI model and the TCP/IP model. So essentially, as I mentioned, they're doing the same thing. Okay, it's handling of data and it's a transmission from one host to another. The application, presentation, and session are actually called all into an application layer, into the TCP/IP model. Transport is transport, network is actually called internet, and the data link and the physical are a single layer within the TCP/IP model. Okay, so again, we just talked about the TCP/IP model. Now we're switching to the TCP/IP protocol. So the TCP protocol is basically a combination between the transport and the network layer within OSI. What happens is TCP is used basically for verifying the correct delivery of data from a client to server using ports. Okay, IP is designed for moving data and actually packets from one host to another. Port. So the easy way to describe a port is essentially a mailbox. So if I want to send somebody a letter, snail mail, we need to know a mailbox number. Okay, so each house has a mailbox number, and we use that mailbox number to establish communication. Now, ports are assigned by IANA, and if you'd like to find out more information about these port assignments, you can visit the link. The most common ports to available ones are the TCP, which is more connection oriented, or UDP, which is connectionless. So the advantage of using TCP is we have error checking, we have reliable delivery of information. It's slower, but we know that there is a verification that something was sent and received. With UDP, we have data bursts. So voice over IP usually uses UDP, where we care about not necessarily the quality or the effectiveness or the verification of the data, but what we care is about sending a large quantity of data as quickly as possible. So it's important to know that we also have TCP flags. So these TCP flags are essentially a punctuation. So if we go back to the example with writing a letter, when we write a letter, we follow specific guidelines or rules that are common and known by pretty much anybody that has some basic writing class and structure. So what's happening is when we start a new sentence, we use uppercase letter. When we finish a sentence, we use a full stop. So this is the same thing with flags. The flags tell us basically when communication is established, when it's torn down, and when there's a priority, and so on. Some typical flags are the SYN, the synchronization, the beginning of a connection, the ACK flag, which is the acknowledgement received of previous transmission, the FIN, which is a closing of established TCP connection, and reset, which is a abort of a TCP connection before it is established. Okay, so the difference between FIN and reset is FIN, you're tearing up a connection that was already established, and reset is you're resetting the connection before that took place. A typical TCP header. So what's happening is we have the source port, the destination, we have a sequence number, acknowledgement, and these are basic representation of that information. Here are the flags. So if you follow the convoluted arrow, this is a basic Wireshark packet capture that examines these flags. And we have the acknowledgement flag. So these are basically zeros, indicating so zero, no or off, one is on. So the fact that we have one here, and this is the only flag that's set, actually tells us, one, we have the binary value 1, and it tells us the acknowledgement flag is set. Okay. So the three-way handshake. So the reason why we're showing this information pertaining to Nmap is in order to understand how Nmap works. Nmap is leveraging this three-way handshake protocol to establish a connection or inquiry from your attacking machine to the host target machine. Okay. In order to understand how Nmap works and to defend against the different Nmap scans, we need to understand what is the intricate relationship, how does Nmap establish that connection. And at the core of all of this is the three-way handshake communication. So what happens is before a client and a server need to communicate is they exchange essentially three handshakes. The first one, so at layer 4 of the OSI model, we have a basic transport transmission, okay? So what's happening is we're saying from the client says, hello server says, hi. Client says, would you like to talk? Server says, let's talk, and then we have connection established. So the client sending an inquiry to the server to say hi and see if the server would like to talk is the SYN basically flag. If the server doesn't want to acknowledge the client, this would not take place. Okay. The server says hello back, or sends a response indicating that the server is willing to talk to the client, and this response is indicative of the synchronization and acknowledgement flag sent back to the client. Then the client acknowledges the response from the server, and the final result is the communication between the client and the server is established. Now, if we examine a different example where there's a disconnection. So in this case, what's happening is in order to terminate the connection, we have a successfully established connection. The client is finished talking with the server. So, for example, we've indicated that taken all information from the web server. We need to close the connection. Then a FIN packet or flag is sent to signal the disruption or the tearing up of the communication with the server. So as the client sends this request to tear up the communication, server responds with acknowledgement and then FIN flag, and then the client says, okay, and at this point the connection is closed. Okay, so this is a different illustration of the intricate relationship between the client and a server. In this example, we're using SSL. And this is kind of important for different certifications that you may pursue, specifically CISP or CEH. This is a very typical question that will come up during those certifications. Now, illustration of a basic client and server communication. So at this example, we have a SYN sent to the server. The server responds with SYN acknowledgement, and then the client acknowledges to basically set up a connection. What's happening is once a connection is established, the SSL comes into play. So what's happening is from the browser, we're going in and we have the SSL protocol. So we're using HTTPS, for example. The SSL client says hello and is sent to the server. The server looks into the protocol version, the session ID, the selected cipher, and into the actual server certificate sends hello back. So the client certificate request is optional. So the server goes back to and respond with server hello back to the client. At this point, there is the establishment of pre-shared master key. So the pre-shared master key created by the client with information from the server sent back to the server. And this master key is used for basically creating of an encrypted session. The server authenticates the client, and there is a generation for symmetric keys to encrypt the actual transmission between the client and the server. Okay, so once these symmetric keys are exchanged, we have established an encrypted communication. So Nmap, going back, in order to invoke the help menu for Nmap, we can now type in Nmap -H from a terminal. Some discovery options and most basic scans are the list scan, which is SL if we have, for example, a text file with pre-populated destination IP addresses. We can do a ping scan, which is essentially a ping sweep of perhaps an entire subnet. We have a P0, which is essentially no ping. PS, which is a port list. This is different examples of scans that we can conduct. The port states. So at the very beginning, or towards the beginning, we're talking about different port states. So there are 6 port states that Nmap can report. In one of the examples, we saw that they're basically, all ports were open. So if we're going back right here. So looking at this example, all ports were in the state open. But in addition to this open state, there's 5 more states. Okay, and this is what we're going over. So the closed state, it means that the host is not up. It's accessible, but the app is not listening, or the port is closed. Filtered. Filtered essentially tells us that there's no response from our Nmap probe, and that's most likely due to a firewall. And what can happen is Nmap is going to retry to get the port state many times. Unfiltered. So the port is accessible, but Nmap can determine whether it's open or closed. And this usually can be done, finding out more about the port state if we use a window scan, a SYN scan, or a fin scan. And open filtered means that it's unable to determine whether the port is open or filtered. And that could be due to configuration in our firewall, or certain elements of the communication are blocked. And closed filtered means that unable to determine whether it's closed or filtered. Again, the same thing. So kind of a trivia. So what port does ping use? Well, it's really kind of a tricky question, because ping is actually an IP protocol, so it uses ICMP. ICMP is located at the network layer, and ports are layer 4, the network layer, or the transport layer, yes. Layer 4 is the transport layer. Ports are located at the transport layer, and layer 3 is the network layer. So what port does ping use? It doesn't use a port. Ping is actually using ICMP. ICMP is a protocol. Okay? So, in a nutshell, there's a confusion between the ACL service, which is different than the ICMP protocol. And what I did below here is to demonstrate. So if we look into the ITSI services and we grab echo, we can see that Echo actually is using port 4, 7, and there's some connections to a different Echo service. So the Echo service itself can be using basically TCP port 7. But this is very different than the ping command. So the ping command is utilizing ICMP. ICMP is basically Internet Control Message Protocol, working with IP, which is at the network layer of our OSI model. So if we go back here, yeah, so we have the network layer here where ports are at the transport. Okay. And here we're starting to look into some examples of Nmap and the different scans and how the communication is actually established. So with TCP connect scan or -S capital T, and please make sure that you specify the options, whether or not they're uppercase or lowercase. So the basic format of the command is, if we're using the command line, nmap space -S capital T, and then we specify the IP address of the host. So what essentially the scan is doing is it attempts to complete the TCP connection. So what we're doing here is we're sending a SYN flag, and then we're waiting for acknowledgement. So we're sending the SYN to our target. The target sends in SYN acknowledgement. Then we send acknowledgement back, and the connection is established. The disadvantage of this particular approach is that it's really not stealthy. It's quite noisy. So something to keep in mind. A different approach is to use the TCP SYN scan. So with SYN, we're only sending a request to establish a connection, but we're not really going in and completing the connection to finish the three-way handshake protocol and establish that connection. So what's happening here is Nmap sends to host port a SYN, Nmap receives from host SYN acknowledge, and then what happens is if Nmap receives that SYN ACK, the port is open, the host is up. Now if Nmap sends a SYN and it receives a reset, it means the port is closed and the host is still up because it receives the reset. Now if Nmap during the scan sends a SYN but doesn't receive anything, it means that potentially the port is blocked by a firewall or the host is not down. Okay, is down, I'm sorry. So something interesting to note is that this particular scan can result in a flood. So if you're looking on your network and you see that there's so many SYN flags or packets with only the SYN flag turned on, there's no there's basically immediate reset after that. You're tearing up the connection without really completing it. Why is that? What are you trying to do? Either it's a buggy application, or somebody's scanning your network. So that's an interesting way to find out if somebody is scanning and potentially targeting your network. Is looking into the SYN flags. How many requests for connections are initiated with the SYN flag turned on, but they're not really completed. Okay, so the TCP ACK scan, so it works in a different direction. So Nmap sends ACK to a particular destination. If it receives a reset, then port is not firewall protected, but may be open or closed and the host is up. So if we send an ACK and nothing, or we receive that there's ICMP unreachable, the port is blocked for sure by a firewall. Okay, so with the fin scan, so if you see fin packets, so there's no reason you should be seeing a lot of fin packets on your network unless somebody's really scanning it. So if you if you see a fin, that's indicative of something fishy going on. UDP scan, it's very unreliable. So sometimes it can be useful under certain circumstances if you're examining or validating some results or trying to find leads and nothing else works. But keep in mind that this particular scan can result in false positives. The stack fingerprinting. So when we're talking about fingerprinting, we're talking about identifying the operating system. So looking into whether the operating system is Linux, Windows, what flavor it is. When we're talking about footprinting, we're talking about network topology mapping, evaluating what is the layout of the network communication between host A, B, and the rest of the examined host for a particular range. So with the -O option for Nmap, it lists the different things that it sends to the target to determine what operating system it's running. Okay. And the way it works is looking to sends all this these different approaches: no packet, SYN, FIN, urgent, and push to an open port, only SYN to a closed port, ACK to a closed port, FIN, push, and urgent to a closed port, and then it gets those responses, looks into a comparative database of those responses, and determines based on this whether or not a particular host is running Linux, Windows, and so on. So the timing. So with the timing, we have different options. And why do we use timing? Well, timing is kind of an interesting thing. So if we go in and we're trying to be stealthy, avoid detection, and reason being that could be that we're examining the preparedness of the incident response team to respond to the attack, or perhaps just the sysadmin, the firewall admin to look into and detect an attack. We want to be stealthy, right? If we're raising a lot of noise and making our presence known, that could be easy for the sysadmin to block us and stop our attack. And we really want to simulate what would an attacker do, right? They'll time basically the scans so that they can blend in with the regular traffic and raise the least amount of suspicion. So by timing these inquiries to the hosts, we're blending in with all the white noise that's taking place in our networks and making the scans less detectable. So by leveraging these timing options, we're avoiding or making our presence less known. We're camouflaging our presence with the rest of the traffic. So looking into here, there is different examples of timing. So for example, the paranoid probe, it's usually probe response timeout 5 minutes. So every 5 minutes we're going to send one packet and we look for a response. It's very, very lengthy process, but it's the most I guess stealthy approach. So what we can do usually is, if you want to get the information as quickly as possible, and we go to the opposite side of the spectrum, we do an insane scan. So this is usually the T5. So if you're doing a paranoid, that's usually the T0-T0. If you're doing an insane, that's identified by the capital T number 5. We're doing a very quick results, but at the same time, what's happening is that some of the information may be unreliable, and our presence could be easily detected. These are some general examples into using, so we can use an IP address or a host name. V is a verbose, a very quick scan. What we're doing here is specifying a range. We can specify an asterisk for a wildcard, or we can define a range. So exclude a host. So what we can do is we can append the -- exclude for a single host or a couple of hosts. Turn on the operating system and service versioning detection. We can use the -A, which is a very aggressive scan. Includes script scanning, so potential for detecting different vulnerabilities. Or we can use some other examples. Find if a host is behind a firewall is the basically ACK-scan. Scan a host behind a firewall is the PN option. Just different examples of scanning. An interesting option is using decoys. So if you're trying to go in and perhaps camouflage where the attack is coming from, what we can do is use decoys. So what we're doing here is we're using Nmap -N, and then where we went, the IP address of no, it looks like yeah, we're using the IP address of our decoys, and then comma the second IP address, comma your own IP address, and then comma the another decoy. So basically these decoys, we're listing our IP address amongst decoys, and then we're specifying the target IP address. Well, what's happening? The target is seeing that there is scans coming from, but it could be coming from one of these 1, 2, 3, 4, 5 sources. And all we're doing with this is we're buying time trying to confuse the defenders into where the actual scan is coming from. So this is just their examples. Again, we are continuing. Something to note is that sometimes when we're trying to evaluate a system, we perhaps may be interested in, if it's the initial discovery process, evaluating all 65,535 ports, okay? And a usual good way to do this is with a -A option, which is really noisy. Or perhaps we can specify, -P and specify port 0 through 65,000 and so on. This will be a more comprehensive examination of the host. Some scans may not be programmed by default to include certain ports. Or perhaps they may be scanning the top 10,000 or 1,024 most common and well-known ports. So some tips, if you'd like to increase the chances of the Nmap packets or inquiries to be admitted into the network, what we can do is use the source port. So if you use -source -port and then we specify the port number, so basically you're saying your traffic is coming from port 25 on a client destined to the target. It's more likely that, for example, a firewall says, okay, allow port 25 for communication through the firewall. If we're specifying that the source port, the information coming from our Nmap scan is coming from port 25, it's more likely it's going to go through the firewall. Okay. The most common ports are 25 for SMTP or 80. So if you're simulating basic traffic, most firewalls are filtering perhaps 80, but port 80 is always open. So if you're camouflaging our traffic coming from port 80, it's more likely that it's going to get through the firewall. Okay. So the decoys we talked about, if we would like to confuse any intrusion detection, we use the -D for decoys. So if you'd like to switch off ICMP pings, which are noisy, we then use the -P0 OS detection. The -F is actually a very helpful scan. The -F can help us to quickly examine a large number of hosts. Okay, so if we have like 2,000 hosts or whatever, we specify the range, our CIDR, and then we do -F, and it gives us a quick inventory of what are the most common things that are open on a particular host and which hosts are alive. So this is helpful for massive scanning. Here are some examples. So in this case, we see Nmap -F localhost. What we're seeing here is that the port state, we see what's open. Over in this example, we're specifying a source port 80. And then for the localhost, so we see slightly different response. Okay, so different examples, different Nmap options can provide different results, and the options are unlimited, how we combine them and so on. Nmap script engine. So with the script engine, we're enhancing the capability of Nmap. Okay, so the script engine is leveraging text files, and these text files are instructions into giving Nmap additional functionality. Okay, so what's happening is we have these scripts located on a Linux system into the USR share Nmap scripts location, or if we're installing Nmap into on a Windows system, this is the most typical location. And all we do is we can go to the nmap.org website, look up a script, and put it into this destination folder for Linux or Windows. And what happens then is we've added the script to the known database. Then all we got to do next is invoke the script. And in order to do this, usually from the source where you downloaded the Nmap script, it tells you what switch, what option you need to use in order to invoke and use that particular script. So this is some additional information about the Nmap script engine. So they can do different fascinating things, including exploitation. The most common scripts are broken down into categories. So you have a network discovery, including NFS, server message block, remote procedure call, vulnerability detection. So very neat. If you don't have a vulnerability scanner, you can't pay for one. Well, we have Nmap to do some basic vulnerability detection. Exploitation. So that could be potential, brute forcing, leveraging Metasploit modules to execute, certain an exploit. Backdoor detection. How fascinating! So if we do a script scan, and in this case, we go in and we're trying to detect, certain instances of a worm or a particular scan, it can detect MyDoom infections, configure worm, you name it. It's so useful. Of course, it's not 100% proof, but when you have thousands and thousands of hosts, using a simple script engine scan to help us look for these infections and potentially identify, infected hosts can be a lifesaver. In order to invoke a script scan, we could use multiple things. So we can specify the dash lowercase s capital C, or we can type in -- script. Okay, so looking in through the examples, what's happening is sometimes we need to invoke an update of the database. So let's go through the basic syntax before we go into updating the actual script database. So if you want to get a detailed usage of the Nmap script engine, you can certainly go to this URL. The basic syntax for a script is -- script, dash help, then the file name, and we can pipe in the category. So here's an example. Script help, we put in quotes discovery, and then we do more to basically get one line at a time, one screen at a time. If we would like to get information about a particular script, like in this case is FTP and identify anonymous FTP login, then we can invoke this script and get help information for this particular NSE script. Script selection, so basically takes a comma separated list of categories, file names, directories. So what we can do is you can specify dash dash script and then the default category and save to indicate that we would like to run only the default set of scripts that are safe. Nmap script SMBOS discovery, so it loads the SMBOS discovery script. And then we don't need to provide the NSE extension. If we're using autocomplete, that may be automatically populated. So in this particular example, what we're doing is we're using a script, default script, we're grabbing a banner, and we're using all NSE custom scripts that are located in this particular directory. So this is an example of how we can bridge different scripts together, different options. Okay, this is additional examples. If you'd like to engage a DNS brute force script against this particular website. Okay. If you'd like to find out virtual hosts that are tied into an IP address, so virtual hosts, like for example, if you have one web server, but the web server, you have multiple websites. Well, these websites could be set up as virtual hosts. So this is a good way, for example, when you're setting up a web application firewall, one of your initial activities would be to go in and identify, what web servers are trying to protect for your web application firewall. Not just the web server IP address, but the virtual host. And this could be a very time-consuming activity if you're not the system admin, right? So from a security perspective, if you can leverage this script, it's really a time-saving tip. And there's some additional examples. So I'm going to pause here and perhaps make another video that actually walks through using Nmap and setting up NSE script that will be able to do a vulnerability scan.